In this video, let us write Maxwell's field equations in terms of electromagnetic potentials A and phi. For this, let us make use of Maxwell's fourth equation. It was written as in Maxwell's third equation here. It was an error. It is not Maxwell's third equation, it is Maxwell's fourth equation, which is given by curl of H vector equal to J plus dou D vector by dou T. Now let us write this equation 1 in terms of E vector and B vector. For this, let us multiply the above equation by mu on both the sides. When we multiply, we get mu of curl H vector equal to mu into J vector plus mu into dou D vector by dou T. We know that B vector is equal to mu times H vector and the displacement vector D equal to epsilon times E vector. Let us replace mu H as B in the above equation. We get curl of B vector equal to mu J vector plus epsilon times mu into dou E vector by dou T. The last term we get when we replace D by epsilon E. So, the curl B vector equal to mu times J vector plus epsilon mu into dou E by dou T. Let us take it as equation 2. We know the electromagnetic potentials are given by B vector is equal to del cross A vector, that is curl A, and E vector is given by minus grad phi, that is minus del phi, minus dou A by dou T. So, the first one is called as in vector potential, the second one is called as the, phi is called as the scalar potential and A is called as the vector potential. So, B equal to curl A vector is taken as equation A and E vector is equal to minus grad phi minus dou A by dou T is taken as equation B. Now, let us substitute the value of A and B in equation 2. When we substitute, we get in place of B, it is curl of curl A equal to mu times J vector plus epsilon mu dou by dou T. In place of E vector, we write minus grad phi minus dou A by dou T. We are all much familiar with this vector identity. Curl of curl A vector is equal to grad div A minus del square A. We have used this vector identity in on many occasions. So, here also we are making use of this vector identity. So, in place of curl A, we can write grad div A minus del square A equal to mu times J vector. So, bringing this minus grad phi minus dou A inside, we get minus epsilon mu dou by dou T of grad phi and minus epsilon mu dou square A by dou T square. The next case what we are doing is we are bringing everything to one side except mu times J. So, we get del square A minus epsilon mu dou square by dou T square. We are clubbing this together and again we have minus grad div A minus mu epsilon dou by dou T grad phi. So, on the other side we will have only minus mu J. It's a just and rearrangement and we could see in the third term and fourth term we have a grad. So, we have taken it as a common, then we get del square A vector minus mu epsilon into del square A vector by dou T square minus grad into div A vector plus mu epsilon dou phi by dou T. Here we have taken the minus as a common, So we get within the bracket div A vector plus mu epsilon dou phi by dou t, that is equal to minus mu j vector. Okay, now we have got a one field equation in terms of the vector potential A. Again we are going to get another field equation in terms of the scalar potential phi. So for this we start with Maxwell's first equation, which we are more familiar with. Del dot D vector is equal to rho, that is div D equal to rho. We know D can be replaced by epsilon times E vector. So we get, taking the constant epsilon outside, we get epsilon del dot E vector equal to rho. And we can bring the epsilon to the other side. So it becomes rho by epsilon in the right hand side denominator. On the other hand, we have div in place of E vector. We write minus grad phi minus dou A by dou t. So multiplying everything, we get del square phi plus dou by dou, that is we are multiplying a minus there all together. So we get del square phi plus dou by dou t of div A equal to minus rho by epsilon. So when we multiply, on the left hand side everything becomes a plus, and on the right hand side we will get a negative sign. So let us take it as equation number 5. So in equation 5, on the left hand side we are adding and subtracting a term mu epsilon dou square phi by dou t square. So to the left hand side of equation 5 we are adding a term, adding as well as subtracting. So that doesn't bring out any effect, adding and subtracting mu epsilon dou square phi by dou t square. So see here we have an added one at the beginning. So del square phi minus mu epsilon dou square phi by dou t square. So other term we have added to the second term of the fifth equation. So on taking the dou by dou t common from it, we get dou by dou t div A plus that added term mu epsilon dou phi by dou t. On the right hand side we have minus rho by epsilon. So we got an equation in terms of the scalar potential or scalar function phi. So this equation number 3, which is written here in terms of vector potential A, and this equation 6, which is written in terms of the scalar potential phi, represents Maxwell's field equation in terms of electromagnetic potentials, that is this scalar vector potential A and scalar potential phi. Here the Maxwell's 4 equations are replaced by two field equations in terms of A and phi. Here A and phi are coupled with each other here.